Begin. Dear Father, we thank you for this day. I thank you for these students who've managed to come to class even though it is the day before spring break. I pray that you'll be with us today. Help us to understand a little bit more about Calculus 2 and, of course, about your creation. Lord, in your name I pray. Amen. All right, first things first, let me explain to you what went wrong yesterday. It's not that complicated, really. So we looked at the difference of Sn and nsn minus 1, right? And so that would be basically the sum k equals to, let's say, m to n of a sub k minus the sum, let's say k equals m to n minus 1 of a sub k. I'm using m as just a starting point for the series, okay? That's the main thing I was not paying enough attention to yesterday. Now, basically the same calculation we did last time goes through, and we do get, a sub what? A sub n. So we've got this identity, a sub n is equal to s sub n minus s sub n minus 1, right? And the critical question that I should have asked myself, and I should have tried to make clear yesterday, because it's the whole issue, for what n does this hold true? For what n do this formula actually make sense? Well, I would argue that this only makes sense if n minus 1 is greater than or equal to m, right? So in other words, we have a sub n is equal to s sub n minus s sub n minus 1 for n equals to what? Well, n equals to m plus 1, m plus 2, dot, 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 dot. This formula does not apply to the base case. Okay, so then, like yesterday, what did I do? I said, okay, so suppose Sn is equal to n squared plus 7, right? And then I said, okay, let's find the series, the terms which are being added to get this, right? And so we worked out that Sn minus Sn minus 1 was what? N squared plus 7, right? Minus n minus 1 squared plus 7. What did we get? We ended up with 2n minus 1 yesterday, right? And I was like, oh, cool, that's an odd number. So this should give me the sum of the first odd numbers. Well, then the thing is, so what is Sn? Well, Sn, right, is equal to, it's equal to, what's equal to? It's equal to the sum, right? K equals to m to n, right? But I can't I can't just put this here, because this formula only applies to the next case on. So, well, I could say a sub n, but that is going to be equal to a sub m, the first term, plus the sum k equals to m plus 1 to n. And now over here, that is where this is valid. So over in this one, I can put 2k minus 1. And I think you can make this go for any choice of m that you like. What's a nice, easy choice for m? I think we should let m equal to 0, let's say. If we let m equal to 0, we have s sub n is equal to, a sub 0 plus the sum k equals 1 to n of 2k minus 1. I mean, there are various choices you could make here, but... And you see, the thing is, a sub 0 isn't pinned down by this relation. You can choose you have to choose a sub 0 to be whatever you need it to be to match the formula that I gave us. So I just made this up yesterday, right? I made it up to try to see if I could actually work this out and see what the a sub n's being added were. Then I got really confused for about 10 minutes, because I failed to appreciate that you need a starting point for the series, basically. So let's see here. What should a sub 0 be then? S0, right, should be equal to a sub 0. Am I right? Because when you put n equals to 0, this is gone, and you just have the first term. But if you put n equals to 0 into this, what does this give you? 7. So therefore, what we have is that n squared plus 7 should be equal to the sum k equals, still getting wrong, 7 plus the sum k equals 1 to n of 2k minus 1. So you can cancel off the 7s, right? And I think you have, right? I mean, you can cancel the 7s here and you get an identity, which is that n squared is equal to the sum, right? K equals 1 to n of 2k minus 1. Now, of course, if you feed k equals to 1 in there, what do you get? 1. Then k equals 2 gives you 3, and so forth. And you can try this out. So, for example, well, I'm sorry, I'm 2n minus 1, right? Let's try it out. So, like, is 5 squared equal to 1 plus 3 plus 5 plus 7? Where do I get to? Plus 9. Is that true? Okay, so today it works. What's the difference between today and yesterday? It's really just I was failing to appreciate the issue that this is true for infinitely many choices of m, but not the first one. The first one in the series you have to pin down by the specific formula. Here's an intuition for what's going on here, guys. A series, right, is akin to integration. It's like a discrete integral. If you take the difference between two things, that's like a discrete derivative. So looking at the difference of Sn and Sn minus 1 was in some sense like differentiating the nth partial sum. What happens when you differentiate an integral? Well, out pops the thing you're integrating. In this case, a sub n. So like differentiation of this is given by that, which gives me the input to the integral. But then the process of differentiation destroys constants. So you lose some information. The information you lose in particular is the 0th coefficient, the 0th term in the series, and that we have to put back in by explicitly applying the initial condition, which happened here. You could look at it this way. But I shut up about it. That's all I have to say about that anyway. So is it clear what I did wrong yesterday? What I did wrong yesterday was I just ad hoc picked a starting point for the series. I had no right to do that, and what the error was yesterday. All right, so with that, let us move on to the limit comparison test once more. What's the limit comparison test today? It says if we have a sub n, or rather a sub k and b sub k positive for all k, and if we have that the quotient a sub k divided by b sub k tends to L, which is greater than 0, as k goes to infinity, then the series with terms a sub k converges if and only if the series with terms b sub k converges. So what that also implies, because If something doesn't converge, then it diverges. Okay, it's like it's an either-or thing. You either have convergence or divergence. There's no in-between. There's no middle ground there. All right? If you're talking about a specific series. I mean, if you were talking about a family of series, you could have some diverging, some converging. But if you're talking about a specific series, it either converges or diverges. And so this is a useful test. Let's see how we prove it. So the proof, it's very pretty. If you have a sub k over b sub k going to L, right? Then you can choose then for epsilon greater than 0 such that what? You want to choose an epsilon. You have choice of any epsilon you like because you have the limit existing, right? So in particular, you want to choose an epsilon such that L minus epsilon is greater than 0, okay? So I'm going to choose an epsilon not too big, but big enough so that L minus epsilon is greater than 0. Now, let me just check myself for a second here, make sure I made the right choice there. I don't want to waste your time. I've wasted too much of it. Where did it go? I've lost it. We're in section 12.3, by the way. I skipped over the integral test. I'm coming back to it soon. Yeah, it says choose an epsilon between 0 and L. Choose an epsilon between 0 and L. I think that, you think about that for a second. Here's 0. Here's L on a number line. If we choose epsilon here, that means that epsilon is, right? So that means that, what would that say? 0 is less than L minus epsilon. In other words, L minus epsilon. Okay. All right. Cool. I'm doing what I'm supposed to. If you think about an epsilon greater than 0, right, such that L minus epsilon is positive, then by convergence of this quotient, right, there exists some, let's say, n in the natural numbers for which what? If you have k, let's say, greater than or equal to n, what do we get? We get a sub k over b sub k, right, minus L is less than epsilon. That's the value of that, right? That's what it means for the limit to exist. For any epsilon greater than 0, we can make that difference small. But if you unwrap this inequality, what do you get? You can trade this for minus epsilon less than the quotient, a sub k over b sub k, minus L less than epsilon, right? And then what can you do? Well, you can add L to both sides, right? Add L to both sides, we get L minus epsilon less than a sub k over b sub k less than L plus epsilon. And so what we're trying to do is we're trying to compare, right? We're trying to compare the series a sub k and b sub k. The thing you'll see in both this argument and also the integral test I'm about to show you guys after this is you end up, you want to look at some inequality which compares the two things, which gives you this kind of sandwiching. And it's almost there yet. All we got to do is multiply by b sub k. Why can't I multiply by b sub k? What did we assume? Here, I assumed that b sub k was positive, right? So this tells me then that L minus epsilon times b sub k is less than a sub k is less than L plus epsilon b sub k. But you see, after I have this, all I got to do is use the basic comparison test. Remember what basic comparison test said? It said that if you have a series and you have another series whose terms are larger than that series, if the terms are all larger and that larger series converges, guess what? The smaller series with positive terms also converges. And vice versa. If you have a series which is smaller than a given series, term by term, at least eventually, then if the smaller series diverges, then certainly the larger series must also diverge, given the series has positive terms. So once I have this, right, I can just break into cases. If the series a sub k converges, right, then the series L minus epsilon times b sub k converges by basic comparison test. Hence, the sum over b sub k converges. Why? Because it's just a scalar multiple times that other series, right? And if a series converges, the scalar multiple of the series also converges and vice versa. In other words, if you can factor out a constant, it doesn't change the convergence or divergence of the series. L minus epsilon here is just a constant. Which inequality am I using? Just to be clear, I'm using this one, right? I'm applying basic comparison test to that inequality. And I've also assumed that this converges, right? Conversely, right, if the sum a sub k diverges, then the series L plus epsilon b sub k diverges. Hence, the sum over b sub k diverges. To be clear, I said by basic comparison test, right? Where I've used that is right here, right? And also right here. Logically, that's where I use them. So if I was writing things a little bit clearer, I should have said that there and then said from that it follows the series b sub k converges, or then in the next steps that diverges. So I did an example. I did an example yesterday on how to use this, and I'll do some more in the future. In the meantime, you can look at examples 7, 8, and 9 in section 12.3 for additional insight in how to use the limit comparison test to study specific problems. I'm going to go over to the integral test now, since we need to talk about that. But before I do, are there any questions about this proof? Okay. It is built, of course, over the basic comparison test. By the way, I gave a more thorough proof of the basic comparison test in section 2 yesterday. I think there's a decent proof in the book too, but all right. Integral test. What does the integral test say? For those of you who came in a few minutes late today, to start a class, we basically just went back and fixed the error from yesterday. So you can look at that. Integral test. What is the integral test? Here's what it says. If f is continuous, positive, and decreasing. On 1 to infinity, then the sum k equals 1 to infinity of f of k converges. If and only if it's interchangeable with the statement that the improper integral from 1 to infinity of f of x dx converges. That's the integral test. So let's try to work on the proof of this. So first of all, the last problem in homework 6, right, was a pretty tough problem, right? And in retrospect, man, I wish I'd been able to give you guys a better hint there. I don't think I gave you any worthwhile hint. I'm sorry about that. But basically, the point of problem 69 was you eventually convince yourself that there's this inequality here. And this isn't hard. I'll draw a picture here in a second. A sub n less than or equal to the integral from 1 to t f of x dx is less than or equal to a sub n plus 1, where we're defining a sub n to be equal to the integral from 1 to n of f of x dx. And I think, and in here, of course, we're also assuming that f is continuous, positive, and decreasing. It satisfies the criteria for the integral test. Let's see if we can't draw a picture to understand why this inequality should be true. So if you look at assume f of x is as stated in theorem, okay? Continuous, positive, decreasing. What's its graph look like? It's something like this, right? So if you calculate from, say, 1, right? If you calculate the integral from, and this is only for certain t. What t is this true for? I think if I remember right, it's for n less than or equal to t less than or equal to n plus 1. So the integral from 1 to, so maybe here's n, right? So what would a sub n be? A sub n would be the integral from 1 to n of f of x dx, right? So a sub n with this setup is this area, right? What would a sub n plus 1 be? Given this, we're defining a sub n to be the area integral from 1 to n. A sub n plus 1 would be just keep going a little bit further, right? Let me go a little bit further still. Let's say this is n plus 1. Right, so that would be that whole area, right? What would this be if t is between n plus 1 and n, well, t is in here somewhere, right? So this area is, right, that area, right? And it's pretty easy to see why that inequality should be true, right? In fact, you could get it from integrating an inequality using a property of definite integrals even. Does that make sense? So that's the hint I should have given you guys for problem 69. This is the hint I should have given you, ideally. And then the question is, what do you do with it? Well, problem 69, what does problem 69 ask? Problem 69 asks you to show that the integral from 1 to n of f of x dx goes to L as n goes to infinity is interchangeable, right, with the integral from 1 to infinity of f of x dx equals to L. In other words, the convergence of this very particular sequence built from area functions is interchangeable with the convergence of this improper integral. The truth of that is not hard to argue once you know this inequality. Let's suppose that if the integral from 1 to n of f of x dx converges to L, then what? That means it's a convergent sequence, therefore it's bounded, right? Right? So what you have then is you have that implies that the integral from 1 to t, right, of f of x dx is less than or equal to a sub n plus 1, where this is less than m, because that's bounded, right? But the integral is increasing as t goes to infinity. So you've got this increasing function which is bounded above. So it follows from just calculus, really. This implies then that the limit as t goes to infinity of the integral from 1 to t of f of x dx converges, right? AKA the integral from 1 to infinity of f of x dx converges, right? What I'm using for this argument, I'm exploiting which part of the inequality? I'm exploiting this half of it. I used it really right here, right? Well, maybe the next one too, but what if, on the other hand, you assume that the improper integral converges? Then what? If the improper integral converges, right? If you have that the integral from 1 to t of f of x dx goes to L as t goes to infinity, which is what it means for the integral from 1 to infinity of f of x dx to converge, right? What does that tell us? Hence, the integral from 1 to t of f of x dx, which is increasing, right, is bounded. Therefore, you have that a sub n is less than or equal to the integral from 1 to t. I mean, this is already given to us from our earlier argument, right, using it again. But this is less than or equal to m, right? But a sub n is increasing and bounded, right? Therefore, a sub n convergent. And that's the claim, that you can trade the limit as n goes to infinity of the sequence for the improper integral converging. Okay. This is not the integral test yet. This is just problem 69. Excuse me. So the integral test then. I have to draw another picture for, okay? So here's the picture we draw for the integral test. I'll draw, I think I can get away with drawing one picture. He draws three in the book, but I think it may be useful to draw just one picture with the three things superposed. I may regret this. We'll find out soon. So here's your function. It's continuous. It's positive decreasing. So that next episode, by the way. We're looking at 1 as a starting point, all right? 2, 3, 4, make a break in the thing, and okay. And so one thing you could think about, of course, is just the area under the graph, right? That would be the integral from 1 to n of f of x dx, okay? But then you can envision partial sums in terms of explicit diagrams of boxes, right? Like, for example, if I look at this guy, right? That was clearly what, since, I mean, and I'm using again that the function is positive and decreasing, right? To draw this picture. But you guys can see as well as I can, the height of this is f of 2, right? F of 3, f of 4, f of n. So that's less than or equal to, so we got f of 2 plus f of 3 plus da 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 dot plus f of n. That's a lower sum for this integral, right? That's an underestimate of the integral from 1 to n. But on the other hand, you can just as well draw these boxes, right? Right? And now you've got, like, overestimation, right? So that's less than or that's greater than or equal to the integral. And what does it start at? Well, the height of this one is f1, right? The height of the last one is f of n minus 1, though. See? So this is f1 plus f2 plus da 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 dot plus f of n minus 1. So the integral from 1 to n is stuck between these two things. Now this inequality is as important for the argument I'm about to give as this one was for problem 69. But we use problem 69 as well. Let me try to explain to you how. So what's the claim of the integral test? The claim is if f is continuous, positive, and decreasing, this converges if and only if that converges, right? So this means both directions are true, right? So we got to assume one side or the other and try to show the other holds. What do you guys want to start with? Let's assume the series converges to start with. I don't know. This way. So suppose the series k equals 1 to infinity of f of k converges. Then what? What does that mean? You can observe, right, that the integral from 1 to n of f of x dx is less than or equal to f of 1 plus da 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 dot plus f of n minus 1, right? Which is what? As n goes to infinity, what does this do? This goes to L. because we're assuming that the series converges, right? So surely the n minus 1th partial sum converges if we're given the nth partial sum, right? Difference n versus n minus 1 as n goes to infinity is washed away, right? So this converges, right? Therefore, by basic comparison test, we have what? We have this sequence of integrals is smaller than a convergent sequence, right? So it follows that what? Oh, I'm sorry. I'm thinking, oh, that's the worst thing. I'm sorry, I shouldn't argue by basic comparison test. I'm an idiot. We're not doing this. Is this a series? No, we're talking about sequences, right? I mean, yes, it's a series, but I'm talking about sequences. I'm sorry. Let's be a little bit more specific. This, if that's convergent, right? Hence, f1 plus dot plus fn minus 1 is less than or equal to m. I mean, if it's convergent, it's bounded, right? So thus, the integral from 1 to n of f of x dx, don't need to tell you guys on that stuff, less than or equal to m as well. So what we have then is we have a sequence which is bounded above. Is this integral sequence increasing? In other words, if I look at the integral from 1 to n plus 1 of f of x dx, right? That's equal to what? Is that less than or equal to, is that greater than or equal to the integral from 1 to n of f of x dx? Why is that true? No, excuse me. We assumed f of x was what? Positive, right? If you integrate a positive function over a larger, or further down, you add things, right? So it's increasing. We have an increasing sequence bounded above. Therefore, by what? Bounded monotonic sequence theorem, right? So what have I shown? I've shown that the sequential limit of this integral goes to L as n goes to infinity. Oh man, that's not what we were supposed to show. We were supposed to show that if the series converges, the integral converges, right? But then problem 69 comes and saves the day. Because problem 69 showed us that the sequential convergence of these area integrals, the sequence of areas, whatever you want to call this thing, this convergence implies that convergence. And so we're done. See, because this implies that the integral from 1 to infinity of f of x dx is equal to L. That's by number 69. So that shows you that if the series converges, then the integral converges. And now we reverse the arrow. We got to do the other direction. Very similar argument. Assume the integral from 1 to infinity of f of x dx converges. Thus, by number 69, the sequence 1 to n of f of x dx converges to L. Hence, the sequence from 1 to n of f of x dx is bounded. And then we go back to our critical inequality. And what are we going to use this time? Well, this time we're going to use this half of it, right? We have f of 2 plus f of 3 plus plus f of n is less than or equal to the integral from 1 to n of f of x dx. So what this gives us is that the sequence of partial sums for the series formed with term f sub k is likewise bounded and increasing, and hence by the monotonic sequence theorem converges. So if this is bounded, right, it follows that this is also a bounded increasing sequence. Therefore, f of 2 plus f of 3 plus da 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 plus f of n converges to L. That's almost what we want. Almost. Because what do we need? We need f of 1 as well, right? Or where did I say? Yeah, f of 1. If that converges to L, surely if you add one thing, if you add a number to something that's convergent, it doesn't change the convergence, right? So therefore, sum k equals 1 to infinity of f of k converges. And so there you go. We have shown that if the integral converges, the series converges, and vice versa. And, well, I mean, I guess this argument is, I guess I could go through two more arguments to show you that divergence gets paired with divergence, but I think I'll spare you those, right? I'll walk you through it intuitively. Like, what would happen if the integral diverged? What would that mean? If the integral diverges, then this sequence also diverges. If this sequence diverges, right, that means you've got a divergent sequence here, right? If this sequence is diverging, it then follows that that must also diverge, right? Because it's a sequence of positive terms. So if you've got something smaller than it diverging, then surely something larger must also diverge. So you can also argue that divergence is paired from one to the other. All right, so we had to work a little bit to prove this, but I think really, honestly, once you draw this picture and you understand what this inequality says, the rest is really just kind of, well, some of you would say math jargon, but it's just trying to tidy up the argument. Really, this inequality is the heart of the proof, right? Once you know that, you really know what's going on. Any questions? Well, let me show you how this works. Look at some applications, yeah? I hate to erase. I'm going to leave this up because I really don't want to write this again. Sorry. So the big application is the so-called, and this is example 1 in the book, and it's my example 1 as well because it's important, the harmonic series. Not many of these series actually have their own special name, but this does, harmonic series. And this guy is the sum k equals 1 to infinity of 1 over k. So what that is 1 plus a half plus a third plus a fourth. Well, you get the idea. Plus dot 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 dot. This diverges. Why? Why does this diverge? Well, here's why. If you look at the integral, well, first of all, let me put my ducks in a row here. If you look at f of x equals to 1 over x, right? This is positive. Right? How can I show it's decreasing? How about this? Check it out. F prime of x is what? Minus 1 over x squared, right? That is clearly less than 0. differentiation is a nice tool to use to prove something is decreasing, right? It should be pretty simple for the things we're looking at because, well, anyway, there it is. It's decreasing. And what else do I need? Well, first of all, f of x equals 1 over x is continuous, right? Okay, so check, check, check. We have met the needed conditions to apply the integral test, right? Continuous, positive, decreasing. Let's do it then. So the integral from 1 to infinity of dx over x is what? Limit as t goes to infinity of the natural log of t minus the natural log of 1. Oh, I'm sorry. I tried to put it in between step in here. Sorry about that. Integral from 1 to t, right? But that works out to the limit as t goes to infinity of ln t minus ln of 1, which is otherwise known as infinity, right? Because while the natural log of 1 is 0, the natural log of t grows without bound. Therefore, the sum of f of k equals 1 to infinity, which is, by the way, exactly the harmonic series, right, diverges by the integral test. It's fun to stop and count the roses here for a second. So if you look at it, if you look at the inequality we have, what do we have? We have like the integral from 1 to n of dx over x is less than what? It's less than or equal to 1 plus a half plus a third plus da-da-da-da plus 1 over n minus 1, right? So that integral is smaller than the n minus 1th partial sum of the harmonic series. So this works out to like ln of n is less than or equal to 1 plus a half plus a third plus da-da-da plus 1 over n minus 1. It's kind of fun. We say that this series diverges, right? It kind of gives you this idea that it goes wildly careening off to infinity, right? But this guy is, well, check this out. In order to get this sum, all right? In order to get this sum to be equal to, let's say, 5. Do you know what it takes to get this to be about 5? If you want to get this to be about 5, it will take you 150 steps. So if you add 1 plus a half plus a third plus a fourth plus a fifth plus plus 1 over 150 or so, you'll get about 5. If you want to make this sum work out to about, let's say 10, the number of steps, the number of things you'll need to add together, something like 22,000. If you want to take enough sums of reciprocals to get to 20, to get it to about 20, you need something like about 500 million.
You say that so calmly.
If you would like to get the sum of reciprocals to about 100, well, you better take some time. You're going to need about 2.7 times 10 to the 43rd steps. If you would like the sum of reciprocals to be 1,000,000, so in other words, you're adding reciprocals until you get them to add up to 1,000,000, that will cost you about 3 times 10 to the 434,294 summands. So yes, this thing is diverging. but it sure takes its time doing it, doesn't it? So this is like the penultimate slowest diverging series. This is like the dividing line between that which diverges and doesn't diverge, typically speaking. What's the next example past this is just generalizing this, right? The so-called P series. The sum k equals 1 to infinity of 1 over k to the p converges if and only if p is greater than 1. How do you know that? Well, proof. First of all, if p is less than or equal to 0, you can use the kth term test. Because 1 over k to the p will not go to 0 as k goes to infinity. So it diverges if p is less than 0. If p is positive, then if you look at f of x equals to 1 over x to the p is positive, decreasing, and continuous. You got a ride? Oh, go for it. When do we? Go on. You're fine. I mean, my class ends right now, right? But okay. It's fine. It's fine. I'm just confused. It was a combination of that and that made me think I was like way over. I'm almost done though, guys. So this 1 over x to the p is positive, decreasing, and continuous. You can show that through explicit details like this, right? If you differentiate f prime of x, you get what? You get minus p over x to the p plus 1, which you can see is positive, right? So it's positive, decreasing, continuous. And the integral from 1 to infinity of dx over x to the p converges only for p greater than 1. Hence, by the integral test, we're done. This is, just like for comparison integration problems, this is like the go-to comparison thing with the P series. It's a very useful family of examples that we have. So anyway, that's pretty much it for section 12.3, you guys. So next time we'll be in 12.4, and I'll just keep moving forward. The homework that was supposed to be due in the past will be due the Friday after break, okay? But there'll be another homework due pretty close after that, probably the Tuesday of the next week. The next homework set will be due. So you would be wise, to work on whatever we've covered so far at least, yeah? Thanks.